inviting me. Yeah, thank you very much for inviting me to come give the talk. So I came to Moscow a few years ago for a workshop, which I guess is similar to one of these workshops, and I really enjoyed my time there. It was really nice, interesting visiting Russia. And whilst I was there, I spent quite a bit of time talking with Andrei Topalin. I'm not sure if he's in this meeting. Okay, he doesn't seem to be in. Ah, he is. He's at the bottom, but his name's in Cyrillic. Okay. Yeah, so I spent quite a bit of time talking with Andrei, and we got some nice work done. Anyway, and I was going to apologize to the speakers. I've got quite a busy day, so I can't really hang around to do the talks, but it doesn't seem many of the other speakers are here for my talk, so maybe I don't feel too guilty now. Okay. So I'd like to start off by talking about the following conjecture, which is due to myself and my collaborator, but we're calling it the Chatrevich conjecture for hypersurfaces. And it's due to myself and my collaborator, Jaman Pekar, from 2017. So it says the following. So it says, let D be greater than or equal to 2, N greater than or equal to 1, and K a number field. Okay, then for all finite sets S of non-zero prime ideals of the ring of integers of K, so the set of OKS linear isomorphism classes of smooth hypersurfaces of degree D in the Pn plus 1 OKS is finite. Okay, so n is the dimension of the hypersurface here. So D is the degree of the hypersurface, n is the dimension of the hypersurface, and the conjecture says there's only finite many hypersurfaces with integral coefficients. Well, okay, it's integral. I mean, like, yeah, I mean, okay, so it's OKS integral coefficients. So there's only finite many of these up to isomorphism. So I'll give you a few remarks. Yeah, so I'm not really sure, you know, the composition of the audience. I'm guessing there's a lot of geometers here. Maybe I'm not sure how many people are familiar with doing number theory. But I mean, if you want, you know, maybe you're really not familiar with rings of integers, S integers and things. Anyway. Yeah, I mean, you could just take, you know, I need some extra flexibility in my talk because I want to like make changes to field extensions, which is why I stated overall number fields. But the conjecture is even completely open, just integers. So it's saying if you look at hypersurfaces with integer coefficients.
Sorry, excuse me, a question. Smoothness, is it important here?
Yes, yeah. At least. Okay, that's a good question. The smooth is important here. I would say yes, but now I'm struggling to think of an exact counterexample off the top of my head.
Okay.
I mean, the conjecture is really about the smooth case. Yeah, good question. Probably won't say anything about. I think that's if we can think of a counterexample in the singular case. Yeah, I mean, there must be. Anyway, okay. So then, what do you mean by linear isomorphism? I just mean isomorphism induced by the ambient projective space. So if you like, you know, I'm considering my hypersurfaces are polarized. I don't care about any abstract isomorphisms. I only want those which are isomorphisms induced by an automorphism of the ambient projective space. Okay, so known cases for this. So the case n equals 1. So this is basically, this is curves as the nth my dimension. and this is due to Faltings. So in this big work, which was with the Fields Medal, and this was more or less the original Chatrevich conjecture. So Chatrevich, yeah, let me make sure I spell Chatrevich correctly. Talk in Russia. So Chatrevich, I mean, in Conjecture's exact statement, he said there's only finite many curves with good reduction outside some given certain places over number fields. And this is what Faltings proved when he proved the Mordell conjecture. And I mean, I'm just looking at plane curves here, so it's a special case. I mean, one needs to be slightly careful with plane cubic curves. Yeah, one needs to be slightly careful with plane cubic curves, but for all the other curves, it's a special case of the Chatrevich conjecture, the original Chatrevich conjecture proved by Faltings. Okay, other kind of cases is like case of quadrics, which is relatively easy. I don't know, in some respects, it must be classical. I don't know who originally stated it. I mean, we proved it just because we couldn't find it in the literature, but it's not too difficult to prove. Some kind of more interesting cases, you have cubic surfaces. So this is due to Tony Scholl. I think this is part of his PhD thesis. Another case, which I think is probably quite close to the heart of some of the people listening. So there's some Fano threefolds, so you can take cubic or quartic threefolds. So this case is due to myself and my collaborator, Aaron Jovan-Pekar. So I wasn't going to talk a lot about this case because I was going to talk about new work, and this is older work, but I know there's people there who really like Fano threefolds. So I'll just say a little bit, I'll just say in words how we do it. So we use the intermediate Jacobian here. So we consider the intermediate Jacobian of these Fano threefolds, and we show that if the Fano threefold has good reduction, then it's intermediate Jacobian. Nice thing is you can construct a model for the intermediate Jacobian over the integers. This was first done by Deline when he proved the Vey conjectures for completed sections of Hodge number 1. Anyway, so that you have a theory of the intermediate Jacobian which works arithmetically. We show that if threefold has good reduction, then so does intermediate Jacobian. And the intermediate Jacobian is an abelian variety. So Faltings tells you there's only finitely many choices for the intermediate Jacobian. And then you need to know there's only finitely many choices for the original Fano threefold. And this is a Torelli, this is a Torelli theorem. Okay, cool. And then some respects, the strongest evidence of all for the conjecture, this is what we did, is it's known in all cases for all hypersurfaces, assuming some standard conjectures. So if you assume the Lang-Voiter conjecture, which is a big conjecture in arithmetic geometry. Again, this is due to myself and my co-author, Aaron Jovan-Pekar. If you assume the Lang-Voiter conjecture, this Chatrevich conjecture of hypersurfaces follows. I'll just say briefly how this works. This Lang-Voiter conjecture says if you have a variety of general type, then it's got, and if the variety needs to have general type, but not only that, each subvariety needs to have general type. And if you have this, then the Lang-Voiter conjecture says that it has only finite many integral points. And we apply this. So there's a way of interpreting statements. This is, I'm going to explain this in more detail later. There's a way of interpreting this Chatrevich conjecture, some statement about integral points on some moduli stack. And we basically apply this Lang-Voiter conjecture, not to the stack itself, but to kind of cover. And that's what we get it to work. But I'm going to explain this stacky framework in more detail later on. Okay, I'm going to give you a warning. This is a nice example. So this is not quite, I think this is not quite answering Yuri Prokov's question, but comes close to it. And it's a nice example. So the choice of model over this ring of integers is important. So I'll explain more. I need that is you really need your model to be a hypersurface in the projective space for the conjecture to be true. So I'll give you a counterexample otherwise. So there exists infinitely many smooth cubic hypersurfaces, smooth cubic surfaces even over Q, which emit a smooth proper model over over Z. Okay, and everywhere I'm looking at isomorphism classes, right? So there's infinitely many isomorphism classes of smooth cubic hypersurfaces over Q, which meet a smooth proper model over Z. I'll explain the construction. It's quite simple. So you take 6 points, P1 up to P6 in P2 of Z, the integral points in Z. Yeah, and then you line general position over Q. Okay, so if you take these 6 integral points, so the data of an integral point is basically a rational point over Q, and then a point modulo each prime. Okay, that's not the exact data, but that's the data you get. So I just want my points, the corresponding points over Q, to line general position, but I don't care the reduction modulo P, they don't need to line general position. This is some respects the whole point. And then once you've taken your 6 points, you take the blow up of P2 over Z in these 6 points. Cool, then this is a smooth proper scheme over Z. Use generic fiber is a smooth cubic surface. Great, and it's clear by construction you're going to get infinitely many isomorphism classes of smooth cubic surfaces here. I mean, you're going to get all the split ones. You're going to get any smooth cubic surface which can be realized as a blow up of P2 in 6 rational points. They're all going to rise this way. There's going to be infinitely many of them. So I think the important point here is I've constructed all these models, and the model, like the reduction modulo P, will be smooth because I'm just blowing up. I'm blowing up, a smooth point on a smooth scheme, so it's going to be smooth. But the reduction modulo P, it won't bed as a cubic surface in projective space. It'll be like a weak Pezzo surface, is what it's called. So in the conjecture, you really need to look at just hypersurfaces in the projective space, and you can't allow weaker models, otherwise the conjecture is false. Any questions about that construction at all? I think it's relatively clear, hopefully.
And can you say once again, so this example of a cubic surface, it demonstrates some kind of bed behavior from the point of view of the conjecture?
Yeah, it's basically, if you want to weaken the conjecture. So I mean, I stated the yeah, so I stated the conjecture here, and so I've told you this conjecture is true for cubic surfaces. Oh, I zoomed in anyway. I told you it's true for cubic surfaces, and what it says is only finitely many smooth cubic surfaces over the integers, say up to isomorphism. This follows this conjecture. But what this example shows is that actually there's infinitely many cubic surfaces over Q which emit a smooth proper model over Z. And the whole point is a smooth proper model won't be given by a smooth cubic hypersurfaces. It will be some different scheme. So that's why you really need to, you can't just allow arbitrary models, because like the original Chatrevich conjecture, it was in terms of like good reduction. So just saying if you want a curve with good reduction outside some given set of primes. So it didn't really impose any conditions on what kind of model you needed over the integers. But I'm saying it's just the conjecture of hypersurfaces, you need to impose conditions on what kind of model you've got. Does that make sense?
So once again, if you understand the conjecture literally, then it doesn't apply to cubic surfaces.
It does, yeah, it does. It does apply to cubic surfaces, but I'm looking at smooth hypersurfaces degree 3 in P3.
In P4.
Sorry, P4. Yes, smooth hypersurfaces degree 3. No, in P3. I'm looking at smooth surfaces. Yeah, smooth hypersurfaces degree 3 in P3. Then there are finally many of them. Yes.
Yeah. So okay. Okay. Yeah. Okay. It's fine. Yeah.
Right. I guess it may be slightly subtle. Yeah, maybe it's a bit subtle construction. I'm saying it's got to be careful. Okay. Where's I going next? Okay, yeah. So now I'm going to talk about the thing I want to talk about today. So due to myself and Javan Pekar and Siddharth Mathura. So I guess it came out on the archive last year. So it said the following. So this let D be greater than or equal to 2, N greater than 1. So we got a few results. I didn't want to talk about all of them. I thought I'd talk about the most kind of general one. So basically, if you assume conjecture 1 holds for this pair, so for smooth hypersurfaces of degree D and dimension N, okay, then your conjecture holds for all hypersurfaces of degree D and dimension M, providing your M is less than or equal to N. So if you prove it in large dimension, you get the result in small dimension. This is what it says. So there's a kind of funny corollary. So if you want to prove conjecture 1 in general, you just have to prove it for Fano hypersurfaces. I mean, our film is much stronger than this, but just a nice way of phrasing it. So if you prove the Chatrevich conjecture for all Fano hypersurfaces, you get it for all other hypersurfaces. Because I'm saying this theorem says, provided you proved it in sufficiently large dimension, the degree is fixed. Providing the dimension is sufficiently large and could be arbitrarily large, then you get it for all smaller dimensions. So you take your favorite degree, you prove it for Fano hypersurfaces of sufficiently large dimension, you've got it for all degrees. Yeah, normally I think of the Fano case as being some other the easy case, in the case of general type as being the more difficult case. But for this conjecture, actually, it just says the Fano case is just as difficult. Okay, so I'll just explain the base idea. This is where cyclic covers enter the picture. So I'm assuming conjecture 1 for this pair D, N. Okay, then I'm going to consider my smooth hypersurface. So I get the number of variables right. I'm guessing will be n minus 1. This is in P n minus 1. So this is be a smooth hypersurface. Degree D. Okay, then what I'm going to do is so I want to apply, I'm doing induction here more or less. I want to apply the inductive hypothesis. I want to apply know it for hypersurfaces of dimension 1 more. Now have I got my variables right? Maybe my variables are mixed up. So this is going to be, yeah, n is the dimension of my hypersurface, not the dimension of the ambient projective space. Okay, so then I'm going to take cyclic cover. So x n plus 1 to the d equals.
So basically, you could replace Fano by Fano of as large index as you want, right?
Yes. Yeah.
Because of this implication.
Yeah. So it's funny. I mean, I found it amusing anyway. Okay, so then I consider this cyclic cover. Now the dimension is 1 bigger, right? So I'll start off with something of dimension n minus 1, and I'm outputting a hypersurface of dimension n, which is what I'm assuming the conjecture for. But yeah, you right away have problems because this hypersurface is not well defined. I know this is one thing that threw me to begin with, because like in complex geometry, it's quite common to take cyclic covers and things like this and just move on without thinking about it. But I'm working over non-algebraically closed field. So it's not well defined. So I can just change my equation for my original hypersurface. I can just throw in a minus sign. I get the same hypersurface in projective space up to to find the same hypersurface. And then you get, the corresponding cyclic cover, I'm sure it's obvious to you, is this. And it's not the same over Q, say, if D is even. So I'll be getting a different cyclic cover even though I didn't change my hypersurface. So something has gone horribly wrong here. And even if you're complex geometry, you should be worried because you have similar problems over like the field C adjoint X. So if you were, okay, maybe you're happy if you've got a complex hypersurface, you take some cyclic cover ramified in it. But as soon as you want to do sort of family, you're already going to start having problems. There's no, there won't be a uniform way of doing it in general. So how on earth do you overcome this thing? So what do you do? So you have to formalize the whole construction. I say have to. I mean, this is what we did because it seemed like the most natural way of doing it. To formalize the cyclic cover construction. Okay, cyclic cover construction. Yeah, using stacks. It seems to be the best way of doing it. And this, I mean, we're not the first to try this approach. So RC and Vistali have a paper, which was very useful for us, where they look at cyclic cover as a projective space in 2004, where they look at some of these stacks, and we kind of expanded on some of their techniques and gave some arithmetic applications, basically. Okay, so now I'll tell you what stacks we're thinking about. Yeah, I'm not going to assume you're experts in stacks. I mean, I wasn't before, so I worked on this paper. I'll try and be relatively informal. I mean, I hope that's okay.
Dan, and can you, I think that we were explaining something like the plan to deal with the Fano case, right?
Say it again, please.
So I just didn't realize how the cyclic covers pop up in the story.
Yeah, I mean, I didn't really fully explain that, but basically, to prove this theorem, we're going to do some kind of induction. So we're assuming the result holds in some case, and we're going to prove in cases of smaller dimension. So what we do is we consider a hypersurface of dimension n-1, and we're assuming the conjecture in dimension n. So we're going to have to associate to this hypersurface of dimension n-1. We're trying to associate to it a hypersurface of dimension n. Yeah.
I see. So you're going to lift it into higher dimension, and the way you do this is by adding a new variable in this particular way, and so that it has a structure of cyclic cover. But we still don't understand from this explanation why is it important that it has a structure of a cyclic cover.
Yes, I haven't explained that yet, but the point is we need some way to go from dimension n-1 to dimension n, and this is the way we're doing it, by adding an extra variable. And the idea is if the original hypersurface was smooth, then this cyclic cover one is going to be smooth, so we can hope to apply the conjecture to it.
Yeah, and then you will need to recover, and then the conjecture, suppose that the conjecture holds for your higher dimensional hypersurface, and then you wish to recover the same kind of assertion for the lower dimension hypersurface.
Yes, exactly.
And that's where you are going to use the cyclic cover structure.
Yes, yes.
Okay, thank you.
No, thank you for asking the questions. Yeah. But I think the problem is this cyclic cover construction, it's not well defined. And this is the first problem we have to overcome. Well, the main problem we have to overcome. And this is what I'm going to explain now, how we overcome it. And we overcome this problem using stacks. Okay, so the moduli stack of smooth hypersurfaces of degree d and dimension n. So it's a relatively concise definition, denoted by h subscript d comma n. So what do you do? So you take Hilbert's scheme. Okay, I'm calling it Hilbert's scheme. I guess it's not strictly a Hilbert scheme, but anyway, Hilbert's scheme of smooth hypersurfaces of degree d and dimension n. Okay, so yeah, so what do you do? I mean, hypersurfaces in projective space, they're just parameterized by the projective space. I mean, everyone knows this. And projective space, the corresponding dimension. And what I'm looking at, I'm just looking at the open subset of those of this projective space, which I'm calling the Hilbert scheme, the open subset which correspond to coefficients who give a smooth hypersurface. Okay, so, and then what do? We just quotient out by the action of the projective general linear group of the ambient space. I'm saying this is related to the fact I'm only considering isomorphisms induced by an isomorphism of the ambient projective space. And since I really want a moduli space for the objects I'm parameterizing, I don't want a coarse moduli space, I want a fine moduli space, I have to take a stacky quotient. This is what square bracket means. So I'm taking this quotient that in the category of stacks, and this is give me a genuine moduli space for the problem I'm considering. And it's nice to think of what the function of points is for this stack. So I'm going to let T be a scheme. Okay, then an element of this HTNT. So yeah, so it's going to be, so it's a diagram. So this could be some scheme X embedding inside P. So this is a, so this P here is a Brauer-Severi scheme. And this morphism is smooth proper. So X is a scheme, everything's picture, everything in the picture is schemes. So Brauer-Severi scheme, you hopefully know what it is, I'll just remind you. So I mean, it's a scheme which et al. Locally looks like a projective space. So it's, if you think it's a projective bundle over T, but it's a projective bundle with respect to the et al. Topology rather than the Zariski topology. So each fiber, it need not be a projective space, it would just be some form of projective space in general. And what is this? So such that if I look at the fiber of any point, so I'm going to take a geometric point. So yes, it's such a blur. So this is isomorphic to the topology. So the fibers of the Brauer-Severi scheme are projective space. So this is a smooth hypersurface. Hypersurface degree D. This is for all geometric points. T and T. And by geometric point, I mean a morphism from an algebraically closed field. Cool. So I think this function point description is actually really nice. It tells you what it's parameterizing. It's parameterizing families of hypersurfaces in projective space exactly like you'd want. But the problem, the whole thing is, it's like parameterizing twisted families. You know, my hypersurface is not lying in a projective space itself necessarily. I need to take into account all possible descent data. This is what the stack framework does. They take into account all descent data. And this means I need to look at twisted forms of projective space. This is what I have to do with Brauer-Severi scheme. So to work with this, you just have to work with hypersurfaces in a Brauer-Severi scheme rather than the projective space. So it's not, yeah, it's not. I think it's a nice description. I mean, we prove this description in our paper by unraveling the definitions, basically. Okay, so I'm not telling you exactly what the full stack is because stacks are really groupoids, and I'm telling you what the elements in this groupoid are. Because the nice thing about stacks is they take into account, they also remember all the isomorphisms between the objects here, which is what we also need. So this is a groupoid. I'm not going to tell you what the isomorphisms in the category are, but morphisms, you can kind of guess them. It's not too important. So they're kind of, I'll just say they're the obvious commutative diagrams. Yeah, they won't say much more about that because it's not hugely important. It's what you naively guess. I mean, an isomorphism is formed which is induced by an isomorphism of the ambient projective space, or ambient Brauer-Severi scheme. And this modulized stack framework is actually really useful for this whole Chatrevich conjecture, and it's a more natural way of looking at it. So I'm going to state a different conjecture now. It's again due to me, my co-author Arjen Jaban-Pekar. So it says if you look at the set of OKS integral points on this stack, so this is finite for all number fields K and all finite set of primes, non-zero prime ideals. Okay, and so I told you already, this is groupoid. So when we say, to say the groupoid is finite, this is what I mean. I mean that the set of isomorphism classes of elements is finite. I mean, in general, the set of elements in this groupoid is going to be infinite, but we only care about everything up to isomorphism. So saying a groupoid is finite, I mean the set of isomorphism classes of elements is finite. Okay, and the funny thing, well, one of the nice things is this conjecture one is equivalent to conjecture one prime. And I wanted to explain the proof. Yeah, I'll explain the proof because it's not useful to do. So this direction is somehow the easy direction. I mean, it's not difficult in general, but the other direction is not too difficult, but it's just some nice tricks. So if we're looking at the set of smooth hypersurfaces, degree D, dimension N, over OKS, and I'm looking at them up to, well, I guess I shouldn't really technically look at them up to isomorphism just yet. So this was the set which was being considered in the conjecture one, so in the Chatrevich conjecture. And this just, I mean, it's just clear from the functor points description, this just embeds inside the set of OKS points of my stack. So certainly if this is finite, then that's finite. If this is finite up to isomorphism, this is finite up to isomorphism. So this is why conjecture one prime implies conjecture one. For the other implication, so I'll take my diagram, so you look at OKS point here. So this is what it looks like. Now I've got my Brauer-Severi scheme, and it has dimension n+1. And Brauer-Severi schemes, okay, so they're parameterized by, the isomorphism class is parameterized by this Azamaya Brauer group, but here, since we're in a nice case, it's the same as cohomological Brauer group. Anyway, it naturally lives inside, and it's an element, you consider it an element of the Brauer group of the ring of S integers of K. And it's not just an arbitrary element, since it's got dimension n+1, or relative dimension n+1, it's a torsion element of order, well, whose order divides n+2. So yeah, I mean, just, for example, conics, conics in the Brauer group, these are, so conics, these are Brauer-Severi schemes of dimension 1. These correspond to 2 torsion elements in the Brauer group. Okay. And nice thing is this is actually finite. So if you fix the torsion in the Brauer group of a ring of integers of a number field, it's finite, and this is part of class field theory. This is fundamental exact sequence for the Brauer group of a number field, and you can read off this finiteness from this. So all in all, this means it exists L over K, some finite extension, which trivializes all of my Brauer-Severi schemes. So I know there's only finite many which can occur, and I choose some finite extension which trivializes them. And by trivialize, I mean gives me an isomorphism with a genuine projective space. So now this is great. So now, since I set my conjecture up to apply to all number fields to begin with, so yeah, so I now just apply the conjecture. So apply conjecture 1 to L, to this larger field extension. So this will tell me if I'm looking at my set of elements in my moduli stack, there's only finitely many after I make this possible finite field extension. And there's one small sort of point one needs to deal with, is you need to make sure 2 hypersurfaces could be non-isomorphic over K, but become isomorphic after you make a finite field extension. So we just need to take into account these, but again, that's not too difficult. So if I have my set of hypersurfaces over K, which become isomorphic when I base change to the larger field L, this whole theory of kind of Galois descent and twists tells you, okay, so I assume this is Galois. I can assume it's Galois. This is clarified by a Galois cohomology group. So the Galois cohomology with respect to field extension L over K, and I need to have put in the automorphism group of X over L. So this is those hypersurfaces which become isomorphic after field extension, and there's only finitely many of them. So this Galois cohomology set, so I guess it's a set of priori, this is finite, and this is because the automorphism group of X is finite. So here I'm using, if I take a hypersurface, smooth hypersurface in the projective space, it's got only finitely many automorphisms induced by the ambient projective space, providing you just have to ignore hyperplanes, which I've done, and you have to ignore quadrics as well, quadric hypersurfaces. So probably I wasn't too careful in my statements, but I told you already at the beginning, quadric case is known, so we can ignore the case of quadrics. So if you look at smooth cubic hypersurfaces with high degrees, these only have finitely many automorphisms induced by the ambient projective space.
And you're actually using that, it's not only finitely many, but it's uniformly bounded in terms of the degree. And
I don't think so. No, I don't think so.
don't you need this group out XL to be bounded by one and the same constant for all x's?
I don't think so, because I'm applying the conjecture after this finite field extension, and this tells me there's only finitely many hypersurfaces after the finite field extension, and then I apply this result to each of these finitely many hypersurfaces.
Yeah. So okay, it may be different numbers, but it's always finite anyway. Yes. Sorry.
Yeah. I don't need any information. If I wanted to try and make these results effective, I would need some information like you say, but I'm not caring about effectivity. And I should add, probably people know, yeah, I mean, want us to be, it's important here, I'm looking at automorphisms induced by the ambient projective space. I mean, you can have like a smooth quartic surface, there's a K3 surface, these can have infinite automorphism group, but still there's only finitely many induced by the ambient projective space. Great, what was I doing? Okay, yeah. So the right thing to do now is to go via this moduli stack framework, because it makes the original conjecture more clear what we're talking about. We're talking about integral points on moduli stacks. And yeah, it gives us more tools, I suppose. Once we know we're working with stacks, you know, we can really, it's clear what geometric tools we can use. Anyway, so now we bring in the cyclic covers. So I'm going to let Y be a scheme. So yeah, I mean, I guess cyclic covers mean, this word cyclic cover is used a lot in the literature to mean different things. I think the thing I'm going to be talking about is the correct thing to do, it might be call it uniform cyclic cover, but I'm only considering one kind of cyclic cover in the talk, so I just call them cyclic cover. So uniform cyclic cover Y of degree.
Sorry.
Hello?
What did you say?
What did I say here? What?
Yes, just what you said.
I'd say, yeah, I'm just giving the definition of a cyclic cover. And I think what I'm really defining should be called a uniform cyclic cover, but I'm not going to keep on saying the word uniform. I'm just going to call them cyclic covers. I'll finish writing the definition, hopefully more clear. So a uniform cyclic cover of Y of degree D is a morphism of schemes X to Y, which locally looks like, so affine locally, it's on the base, locally on the base, so basically spec R, and it just looks like extracting an rth root, sorry, dth root, a dth root of some element. So this is for R in R. So locally, the equation just corresponds to extracting a dth root of a given element. And then the branch locus is locally given by just setting I equals 0. Now, okay, so what we do in our work is we consider moduli stack of cyclic covers of projective spaces and use them. So the moduli stack was originally defined by RC and Vistali. So there's a way, yeah, probably I'm going to try construction of this moduli stack. I'll just tell you that it kind of exists, well, because I haven't got a huge amount of time left. So I won't tell you exactly how to construct this moduli stack, but I'll just tell you it exists basically. And the functor points is what you would somehow guess the functor points to be. So there's a moduli stack. Moduli stack of cyclic covers of Pn plus 1 of degree D, ramified along smooth hypersurfaces of degree D. So this is what I'm calling this moduli stack. So it's C subscript Dn, so C for cyclic cover, so cyclic cover projective space. And it comes equipped with a natural map to the moduli stack of hypersurfaces degree D and dimension n. And the map is just given a cyclic cover, you just map it to the branch locus. So I think this picture already clarifies a lot of what a cyclic cover is. So the problem was earlier, what we were trying to do was we were trying to go from a hypersurface. Yeah. We were trying to go from a hypersurface to a cyclic cover earlier. And you see, actually, the natural map is the other way around. The natural map associates to a cyclic cover its branch locus. And in general, it's not clear if there's a map going the other way. And it's in fact one of the things we proved. So it's me and my co-authors. So if you want to know whether this morphism emits a section, so this happens if and only if the greatest common divisor of D and N is equal to 1. So the degree of the hypersurface needs to be co-prime to the dimension of the hypersurface for this morphism to have a section. So what this means, I mean, in general, is if this greatest common divisor is bigger than 1, so there's no way to uniformly, so like for all families of hypersurfaces you could imagine, so no way to uniformly write down cyclic covers ramified along arbitrary smooth families of hypersurfaces of degree D and dimension n. Yeah, so in this case, you can't. It's just impossible to be able to write down, to make some canonical choice. You know, this might be the way. Say, you know, earlier in the talk I explained right at the beginning, you choose a cyclic cover. Okay, great, but there's some choice made, and you might want to try and we just try and make some clever choice for all hypersurfaces at once. This proposition says this is impossible. You can't do that in complete generality. I'm not going to explain the proposition. Basically, we need to know some information about the Picard group of these moduli stacks. And this choice of constructing a uniform cyclic cover, there's another way of thinking about it in terms of asking whether some line bundle is divisible by D. So we have to calculate, so asking this to lead to some calculations of the Picard group we use of these moduli stacks and try and divide this line bundle by D and show this is more or less equivalent to, be able to divide it by D uniformly is more or less equivalent to the existence of section. That's roughly how the proof goes. I don't want to explain it in too much detail. I've got time for my arithmetic applications. Great. So now I'll talk about theorem 2, which is the main geometric input we need to prove our original result theorem 1 on the Chatrevich conjecture. So this is again due to my co-authors and myself. So we need to avoid some finite set of bad primes. So it's just those primes dividing the degree D. Then you look at this map, which associates to a cyclic cover, the corresponding branch locus, and we need to invert these finitely many primes. Yeah, this was false otherwise. To invert these finitely many primes, so this map is proper et al. So the map is associated to, it's funny because each cyclic cover itself, it's not et al, right? It's ramified. But the morphism of stacks, which associates to a family of cyclic covers, the family of branch loci, this morphism is et al. I think I quite like. And this is great because we're going to use this to perform some descent. Once we've got something's proper et al, we allow us to perform some descent. Yeah, so I'm just going to give like a sketch of a proof. I mean, I hope that's okay. So you consider the moduli stack of Brouwer-Severi schemes. Oops. Of dimension n+1. So these are the ambient spaces for our hypersurfaces we're considering. Okay, so we look at this. So I need to invert S everywhere in the proof. I just won't write that, so I hope that's okay. So I remind you all the points are here. It's a diagram which looks like this, where I've got some family hypersurfaces in Brouwer-Severi scheme. And what I'm going to do is I'm going to map it to the Picard stack of my moduli stack M. So I map it to the pair, just the Brouwer-Severi scheme, and then the line bundle on the Brouwer-Severi scheme, determined by my family of hypersurfaces is X. So it's just a pair. The Brouwer-Severi scheme is line bundle. Okay, so yeah, maybe I'll draw the diagram and explain a bit more. And there's a natural on this Picard stack, there's a natural map. So the Picard stack, okay, everyone knows what Picard group is. Picard group is isomorphism classes of line bundles. The Picard stack is just the groupoid of all line bundles. So it's the elements are line bundles, and the morphisms are isomorphisms between them. So it's just a stackification of the Picard group. We haven't quotiented out by isomorphisms yet. That's all. And it's useful to keep track of these morphisms because I'm dealing with groupoids. You know, my stack is a groupoid. I don't want to pass the isomorphism classes immediately. So there's a map which just takes a line bundle to its dth power, the tensor dth power. And then what turns out to be the case is if you take the pullback in this diagram, you take the phi product, the pullback you get is exactly the moduli stack of cyclic covers. And this is a map which associates to its branch cover. So this diagram looks pretty fancy. More or less all it's saying is to associate the map to give a cyclic cover ramified in hypersurface degree D, it's the same as choosing a dth root of the corresponding line bundle. This is what they're saying. This is equivalent way of thinking about cyclic covers in terms of dth roots of line bundles. And then this map is proper et al, at least away from its finite set of places S. So this map again looks kind of fancy, but it's not too complicated. So the points here, this Picard stack. So I'm just looking at Brouwer-Severi scheme. So locally, point-wise, it looks like the Picard group, which is just Z. But we also need to remember it's a groupoid. So we need to keep track of isomorphisms. So this is the classifying stack of G, BG, which keep track of the isomorphisms. And then multiplication by D on here, on this Picard stack, it's just multiplication by D on Z, which is obviously proper et al. And it's multiplication by D on this BG. Okay, maybe if you don't know too much about stacks, it's not clear, but this is going to be proper et al. Away from my finite set of places. Proper et al. Away from S. So then we're pulling back something which is proper et al. So it's proper et al. Cool. that's how the proof basically goes. Great. And now I'll just finish up by explaining how the proof of Theorem 1 goes. So this is a theorem I stated right at the beginning of the talk. And I'll maybe remind you of the statement. Well, we've got the stacking reformulation of the statement. This is the one we need to prove. So it suffices to show that. So the statement of the Chatrevich conjecture, maybe I'll get my ends in this way, yeah. So as I explained, the statement of Chatrevich conjecture for hypersurfaces, it's equivalent to asking that the set of integral points on this stack is finite. So this is the case of dimension n+1 I'm writing here. So if you've got finiteness in dimension n+1, this implies finiteness of the set of integral points in dimension n. So this is what we need to show to prove the theorem. So we're going to pass by these cyclic covering stacks. So this is the n. So this is the map which associates to So this is the map I already told you about, which associates to a cyclic cover its branch locus. And as I already told you, one of the results of proof is this is proper tal away from S. Yeah, so I should clarify. To prove these finiteness statements, you're always allowed to increase the set of places S. It's some nice flexibility, you know. You increase the set of places S because it's going to just increase. It's just going to make this set larger. You'll have more integral points. So it's going to make showing finiteness just more difficult. So you're always allowed to increase the set of places S. So you can always assume D is invertible in here. So this is proper tal away from S. Okay, so that's what we proved. That's theorem 2. Great. But then there's another map to this modularized stack of hypersurfaces now of dimension n+1, where you take a cover, so a cyclic cover. So I told you already, the cyclic covers, I mean, the definition, it's just locally, it looks like taking a dth root of your equation. And it's clear just from the definition, locally it's a hypersurface. Right, so if you take a hypersurface, I'm going to zoom back, I mean, so I told you what it is. If I started off with a hypersurface in the projective space, well, so if R is the equation of a hypersurface in projective space, this cover is going to be a hypersurface, at least locally. And that's how my stacks are set up. You know, the functional points on my stack, these living Browser-Very schemes. Anyway, so the stuff which are locally hypersurfaces. So this is going to also be a hypersurface, just because by definition, the equation gives you a hypersurface. Yeah, so there's a cyclic cover, just so you just view as a hypersurface now. View as a hypersurface in the projective space. And this is again, just goes back to the construction I mentioned right at the beginning of the talk. If you just view a cyclic cover as a hypersurface in its own right. But now we've got the arrows the correct way around. We've got the arrows the right way around in our diagram. We know exactly how they're all related. So then, and this map is it's not too difficult to show. This map is an embedding. Well, maybe we need to be slightly careful. The automorphism groups might be slightly different, but it's up to finding many choices. It's not a problem. Anyway, it's an embedding on isomorphism classes. So I know that I'm assuming this is finite. So since this is I'm just embedding, so a subset of a finite set is finite. So this implies now the integral points on the modulo stack of cyclic covers is finite. Great. So we've managed to show the set of integral points here is finite, and we want to show the set of integral points here is finite. Okay, and the image, you know, now if I look at, I've got something finite here. If this map was surjective on points, we'd be happy, but it's not. It's not surjective on points in general. Yeah, because there's no section. They're saying this map doesn't have a section in general, so this map won't be surjective on points. So we use the factors proper et al. To perform a descent. So I'll just explain what we use. Now I'll write down the result. I won't prove it because I think I don't have time, but I'll just write it down if that's okay. So this is due to Ariane Javan-Pekar and myself. This one, I think it just appeared this year, 2001. And it's a version of Chevalier for stacks. And it says the following. So it says let f from x to y, set to y, be a proper et al. Morphism of stacks over OKS. So I'm going to assume the set of OL S integral points is finite for all number fields of all field extensions of K. Then the set of OKS integral points on original stack is finite. So it says, providing you know finiteness, so you want to prove finiteness of the points on Y, and you know finiteness of the points of X, but you know this over every field extension. Okay, so we know after every field extension. And if we know morphisms proper et al, then we do get finiteness of points on Y. And we apply this because we're assuming the conjecture holds. Yeah, we're assuming the conjecture holds over all number fields. And maybe I'll just briefly say how this proof is proved. There's kind of two cases. So the classical case, we look at morphism of schemes and say this is the Chevalier-Bay theorem. It all existed for schemes. It's more or less the same statement. And there you look at the fiber of an integral point, and it's going to be some finite et al. Scheme, and this will correspond to some number field which is unramified outside some given set of places. And here there's a theorem of Hermite-Minkowski which tells you there's only finitely many such number fields. So that means there's only finitely many number fields which provides this way, which gives you finitely many integral points. The next case we need to consider is when this morphism is a gerb. This is the exact opposite case. In this gerby case, what we have to do is we have to prove basically some version of Hermite-Minkowski theorem for stacks, which says something like there's only finitely many proper et al. Stacks and ramified outside some given set of places. Anyway, I think I've run out of time, so I'll stop there. Thank you.
Thank you.
Any questions? If not, I have a couple of questions. So first, well, apparently there was a proof of the theorem which you announced, but can I just check that? I just want an informal explanation of one step. So as far as I understand, so your strategy is to construct, so you take a hypersurface in low dimension, construct another hypersurface of dimension 1 higher, and then you know that the number of hypersurfaces of dimension 1 higher is finite under certain conditions which are there in Chatrevich conjecture. And then you want to deduce that the number of possible hypersurfaces of low dimension is also finite. So it means that you have to be able to recover a hypersurface of low dimension from its finite cover. So this would be possible if you knew something like that there is only a finite number of finite cover structures on a given hypersurface of higher dimension. Can you explain this step in in simple terms?
Yeah, I think basically the number of choices for cyclic cover structure it's a torsor and mu d basically. it's a mu d torsor. So there will be different choices for the cyclic cover structure.
No, you mean that if you start from a hypersurface of dimension n-1, then there is a kind of mu d numbers, mu d cyclic covers of this branched.
Yeah, sorry, it's more than that. It's yeah, sorry, it's
but you need it another way around, right?
It's yeah, so the set of cyclic covers with given branch locus, this is what you're asking about. The fancy way of writing it, so suppose I'm working over field K. This is the fancy way of writing about it, because each cyclic cover is more or less a mu d torsor. Yeah, each cyclic cover is basically a mu d torsor, at least generically. And so you're looking at the set of all mu d torsors. This is the fancy way of writing it, but like the non-fancy way of writing it, you could writing in Galois, well, I don't know. So it's just set of mu d torsors up to isomorphism, which for like you could write in terms of Galois cohomology, it's this, which by comma theory is just this. So the set of non-zero elements of your field modulo d powers. Is this what you're asking?
No, I think that do you get it right that you are describing all the cyclic covers with a given branch divisor?
Yes.
But I think that we need something like another way around. So what are we afraid of? I think that we are afraid of the situation when you, for any hypersurface of degree n-1, you construct a cyclic cover, and all the cyclic covers for all possible hypersurfaces of degree n-1 suddenly become isomorphic.
Yeah.
And then there's a finite number of these cyclic covers, but still a large number of hypersurfaces of degree n-1. So informally speaking, we must be afraid of such a situation. And I think that whatever you prove, it should explain that such situation is not possible.
Yes.
So that in other words, I think that one has to explain that if you already constructed a cyclic cover, then of dimension say n, then the number of structures of a cyclic cover on this given n-dimensional variety is finite, up to something. Yes,
yes, this is true. I mean, I know in the case of degree 2, I mean, there's a unique choice of cyclic cover structure for degree 2. This is kind of well known, and it's because it's yeah, in degree 2 there's a unique choice of cyclic cover structure. In the other degrees there is finitely many. It'll be something like 5D maybe. Yeah, the number of cyclic cover structures will be something like the automorphism group of mu of D, which is order 5D, something like that, I think.
Well, I think you can argue that, so if you have a hypersurface of this high degree, then every cyclic cover structure gives you some automorphism. And you know that the number of automorphisms is finite. Well, maybe you have an automorphism induced from the ambient projective space, and you know that the number is finite. Yeah, I see. And maybe one other small question: is it really crucial that you are working with hypersurfaces, say not complete intersections or something?
Yeah, that's a good question. I don't know really. I don't know how to get this construction to work. Like, you know, complete intersection 2 quadrics is a really nice case. I don't know. I mean, the whole point with this, you've got purity of the branch locus, so the method definitely breaks down. But the conjecture, yeah, I should add, yeah.
Can you say once again what does break down here?
I mean, you can't look at a cyclic cover projective space, you know, ramified in a complete intersection of higher dimension. You've got the purity of the branch locus, which I guess you know. But the conjecture should still be true, the Chatrevich conjecture. So I've stated here for hypersurfaces, we proved using Langvoiter that it is true for complete intersections. You just have to be careful of some degrees. You have to be careful with multi-degrees. But the whole framework, the Chatrevich conjecture framework, does exist for complete intersections, and I've proven some more cases of this, like in intersection of two quadrics, dimension 3, so Fano case. There's a finiteness statement there as well. Is that what you're asking about?
Yeah, more or less. But so can you, for instance, argue inductively, like you have a complete intersection, and for instance, of two hypersurfaces, and so you already know pretty much about Chatrevich conjecture for the first of these hypersurfaces, and then you can take a cover of this hypersurface branched in the intersection with the second hypersurface.
Oh, I see. That's a good idea. Yeah, I didn't think of that. That's a nice idea. Okay, so you take cyclic covers. You take cyclic cover of a hypersurface branched over another hypersurface. That's what you're suggesting, are you?
I think yes.
Yeah. That's a really nice idea. I didn't think of that.
Okay,
cool.
at least it's unclear that it works.
Yeah, I'm trying to think. I don't see obstruction, because this whole, I mean, I've written it in terms of moduli stacks of cyclic covers of projective space, but the whole framework does apply much more generality. This is something we did in our paper. Yeah, it's a really nice idea. Thank you. Yeah, that could work. Yeah, thank you.
Okay, any more questions? Then let's thank Daniel again. And let us resume in 15 minutes. So we're waiting for Marta Pieropan with Campana points.
Okay, thanks everyone for the invitation. Have a nice rest of the day. Bye-bye.
All right, so I will first introduce component points and then tell you some properties, conjectures, and heuristics about them on toric varieties. Today I work only on toric varieties, so let's start by fixing the sum notation. So to define my component points, I need three types of ingredients. I need some arithmetic setting. So typically for me, this is fixing a number field. And the ring of integers. But for the purpose of just defining component points, we could just think of some Dedekind domain and its fraction field. So in particular, if you want, you can think more in more geometric terms. Instead of K, think of the function field of a smooth affine curve. Say something like spec OK, and then you see the relationship between the two. All right, so we have our arithmetic part of the setting, then we need some geometric parts, some variety to work on. So for me, this will be toric varieties. So X is going to be a smooth, proper toric variety defined over the field that I just fixed. And now we know that toric varieties are defined by some combinatorial data. So it's defined by a fan, sigma. And recall that a fan is a collection of rational polyhedral cones. Such collection is closed undertaking faces of cones and undertaking intersections of cones. And then each of these cones corresponds to an affine open subset of my toric varieties. And the way these affine opens are glued together is prescribed by the fan. So this is the combinatorial data we have. And out of this combinatorial data, we're going to keep our mind fixed on the one-dimensional cones. These are the rays. So sigma of 1 is going to be my set of rays, rho 1 up to rho s. We just give them some names. And for each of these one-dimensional cones, there is an associated toric invariant divisor, which I call the I. The toric invariant divisor on X corresponding to or defined by rho I. And then I'm going to give also some notation to the union of these, D1 union to ds. This is the toric boundary of my toric varieties. The complement of this toric boundary is the open torus orbit. Yuri, your microphone is on, I can hear you. All right, so this is the first part, but now I fix both a field and some ring inside of it. So I'm also going to construct a model over this ring. So my curly X is the toric OK scheme, which is defined by the same fan. Sigma. And this is, because of the choice of sigma, this is a smooth, proper model of my variety X over OK. And we're going to work on this model. On this model, we also are going to consider curly di, which is the closure of the I in the model, or if you want, this is the toric invariant divisor in the toric OK scheme defined by this fan sigma. And I'm going to also have curly D, which is just the union of the curly di's. So D1 union up to ds. It's a lot of notation. But this is my geometric part of the setting. And then to define component points, I still need some to fix some parameters. So this is the last piece of data. I'm going to fix an S tuple of integers, 1 up to s. And these are positive integers, which I just fixed. And using these integers, I'm going to define another piece of combinatorial data, a divisor dm, which is now the effective divisor sum 1 from 1 to s of 1 minus 1 over mi as coefficient of curly di. And of course, I can do the same by taking the generic fiber. I'm just looking at the same thing over K. All right. So now this divisor is also called the Campana orbifold divisor, or you can recognize it from the rational geometry. It's a divisor with standard coefficients. We are going to define the set of Campana points over OK, so OK Campana points. On the Campana orbifold curly X and curly dm. And the set of Campana points on this orbifold is defined as integral points with special properties with respect to the boundary divisor. So with notation, this is xdm of OK. And precisely, it is defined as the set of OK points. Now, curly X is proper, so OK points are the same as K points on this curly X. And we choose such points, we look at them as integral points, and then we look at the condition for each boundary component, so I from 1 to S. We are going to require that if we look at the pullback of the boundary component di under the morphism from spec OK to curly X, which defined my OK point little x, then this pullback, which is going to be an effective divisor, then I write it down with coefficient over P. Here P runs over, if you want, the primes of my ring OK. And the condition is that the coefficient of each of these components is either 0, or if it is not 0, then it is at least mi. And this is true for every component P. So for every prime divisor on spec OK. Okay, so what we do, we take every component of the boundary on the variety or the model we chose. We look at the pullback under this map from spec OK to curly X. It's an effective divisor, and we want this effective divisor to have coefficients at least mi. And this has to be true for all coefficients, and then for all boundary components di. Another way to consider this is to look at
Marta, and can I ask,
yeah.
so is it really important that we are considering all our varieties over some ring?
Well, this condition doesn't make sense if you work over a field.
So what are you doing here? So you're taking a point on a toric variety, and then you take a pullback.
I'm taking a point, something like this. Okay. And here inside I have my divisors. And then, well, there are two possibilities. Either the point is contained inside the divisor, and this is something that I don't want to happen. And or the point is not contained inside the divisor, but it may intersect the divisor at some special points, at some close points of this. This is a Dedekind domain.
And so
and so what I'm asking is that when so if I call this map X, then here I have this pullback. This is an effective divisor. It's not the whole thing. That would happen only if the image of spec OK is contained in di. And then I'm looking at this. I'm looking at this divisor and looking at these coefficients. So there is a unique representation as a sum of prime divisors. And I'm looking at this coefficient and I'm telling I want this coefficient to be high, which is the same as saying that whenever the image of this map intersects di at some prime, then this intersection has very high multiplicity.
So there is some tangency to every component of the toric divisor, which it really intersects.
Yeah. So either there is no intersection, and that's fine, but if there is some intersection, then I want my intersection multiplicity to be high, and as high, how much high, that's prescribed by the multiplicity mi that I fix.
And will you illustrate this notion by some example later?
Yes.
Oh, great.
Yes, so what I wanted to write down now was an alternative way to write down this sum. So when we write down this pullback, we can actually write down explicitly what these coefficients AP are. So what we get is a sum over prime divisors, and then here we have that these coefficients are P. So valuations in the discrete valuation ring of this prime divisor P that I fixed of some Fi, and here Fi is a local equation of for di at the point x and inside curly x. Okay, so let's try to see this on an example. Perhaps I can write here. So I'm going to do the easy example, which is the projective space. And if you want, the projective space is given by this fan here. Row 0, row 1, and row 2 are going to be the names of my arrays that corresponds to the coordinates x0, x1, and x2 in the projective space. And then we have that these divisors that we're looking at, the di curly, or even the curly di, these are just asking one of the corresponding coordinate x side is 0. So these are just the 3 coordinate lines in P2. And okay, so we are trying to look at the Campana condition. So what happens? We want to do our pullback. In our case, a local equation for di in the integral model of P2, which is just P2 over my base ring. And if you're not familiar with the number fields, perhaps I should have said this before, then you should consider k to be the rational numbers and OK to be just the integers. At some point later in the talk, we will focus on this case only. So what we are asking for here is, let's look at a local equation around my point. So we fix a point, and then a local equation for di is going to be just xi divided by L, where this L here is some linear form, such that L of the fixed point is 1. So we say, we look at the principal open subset of P2 defined by L being non-zero, but if we look as this principal open subset as a subset of P2, say over Z, if we want the integral point X to be contained in such an open subset, then the condition is really, it has to be one linear form that satisfies this condition. Otherwise, the point is not contained, fully contained in the open subset. So this would be a local equation on such an open subset for my point. And the nice thing that we realize, if we look at this, is that, okay, I'm going to now finish up the example in here. So the set of Campana points on P2 with some parameter M0, M1, M2, say over Z, so that it's simpler to write down. Then it's going to be okay. Yeah. Let's just write it like this. So Z points on P2, in particular x0, x1, and x2 can be chosen to be integers. And to have the possibility that there exists a linear form like this, such that L of x is equal to 1, then it makes sense to assume that x0, x1, and x2 are co-prime. Otherwise, we don't have one such. So the GCD of x0, x1, and x2 as representatives of the point is 1, and we can always find such representatives. And then the condition, the Campana condition is asking that the p-adic valuation of xi is 0 or at least an I for every I, and for every p, which now is really a prime number.
Sorry, and what's mi in our case?
Mi is fixed.
Yeah, so it's also a part of the data.
It's part of the data, yes. We fix the parameters in order to be able to define Campana points. Are there any more questions about this, the technicalities of this definition?
So, for instance, suppose that so D is some device supported on the T invariant. It's some T invariant divisor, right? So, suppose that we choose all mi's to be equal to 1.
Yes, that's my next remark. So we have two things to look at to be able to relate this to what we know. So this is true in the example, but also in general. If we take mi equal to 1 for every I, then what happens is that this divisor dn is 0. We also have that if we look at this condition, we say that the periodic valuation of something is 0 or at least 1. And that's going to be true because this something has a periodic valuation at least 0 being an integer, and the same also in the general case. So in particular, we have no condition. So in this case, we have the set of rational points. Which is the same as the set of integral points without any conditions with respect to the boundary. And this is because I chose my model to be proper, so I can do it. So mi equal to 1 gives no condition. And the other extreme case is, well, what happens? So if I increase my mi, I get smaller and smaller sets. I get more and more restrictive conditions. What happens if I take the intersection of all such conditions? So I take Campana points with respect to m, and the intersector for all possible parameters m. And recall that these m's here are just as tuples of positive integers. So this intersection ends up being the set of integral points in the complement of my divisor D. And why is that true? Because we take my conditions, and the condition is that either it is 0 or it is at least mi. This thing on which we are imposing the condition is an integer, and we ask either 0 or bigger equal than m for every possible positive integer m, which means that the second possibility for this condition cannot be satisfied, and so only the first one can be satisfied. And this part of the condition is just the integrality condition with respect to the given boundary component. So if we intersect all these sets of Campana points for all possible parameters m, what we are left with is the set of integral points, which is contained in each of them. And in our case, because we are working with a toric variety and because of the choice of the boundary that I got, this is not extremely interesting, but okay, it's some set of units. So these are integral points on the torus in this case. So units. All right, so now I'm going to lift these definitions to the universal torsor. First, let's try to analyze this condition a little bit better. Oops. So this condition, the periodic valuation is either 0 or at least mi, means that now we're talking about some integer xi and some prime number p. This condition means that if p divides xi, then p to the mi needs to divide xi. This is what it means. And this is also known in number theory as the definition. We require the integer xi to be mi full. So in order to lift to my favorite torsor, I'm going to recall the Cox ring of a toric variety. So I'm going to find the model of this Cox ring over my ring of integers. And it is just a polynomial ring in S variables where each of the variables corresponds to one of the rays. And then using this Cox ring, I can define a torsor, which for me will be denoted by curly y. And it is just a spectrum of this Cox ring, so the affine space, A to the S. But not the whole of it, it's an open subset. And the complement is defined by certain monomials depending on the maximal cones. Of my fan, so it's a combinatorial piece of information. And here the notation means that this d sigma is nothing but sum for all the rays that are not in a given cone sigma of the corresponding torus invariant divisor, and y to the d sigma is just some compact notation for the monomial. We take product over all the coordinates, and then the exponent of y rho would be the coefficient of the rho in here. So in this case, it is 1 or 0, 1 if rho does not belong to sigma 1, and 0 if rho belongs to sigma 1. It's not extremely important to know precisely which one this is, but in any case, we do have the example of the projective plane where we do have A3. And then the set that we are removing is just, in this case, V of x0, x1, x2, which is the origin. And this is my torso. And it has a map down to the original toric variety, in this case, V2. And this is a GM torso. And in the general case, we have a map from Y to the toric variety, which is a GM to the R torso, where R is the rank of the Picard group of the toric variety. So I call this torso morphism pi. And I'm going to tell you what the pre-image of the set of Campana points look like on Y. So points on Y with coordinates y1 up to ys, integral points on Y that map down to Campana points are precisely those that satisfy the condition yi is mi full for every I. Okay, so let's go back a moment. Here we have this mi fullness condition. So I think that I should have added one thing. So if we require these conditions on the, well, divisibility by primes, let's say, or periodic evaluations for every prime, this is our M fullness condition. Okay, so essentially what we are doing, we are looking at points with coordinates y1 to ys that are integers. The reason being that y is an open subset of some affine space, so the points can really be written very simply as tuples of integers, and then we give some condition to each of these coordinates. So that's a very simple description in the case of toric varieties. And this is my arithmetic condition, if you want. So I'm looking at points on this open subset of my affine space, so my torso, and I add this arithmetic condition that the points should be and should have coordinates mi full for every I. All right, so why do we care about these points? Well, the first reason is what I mentioned before. If we choose our parameters carefully, we can have the whole set of rational points. We take mi equal to 1 for every I. Or if I want to get integral points, I should have to take, let's say, in quotes, mi equal to infinity for every I. I've not written down this precisely, but we think that we can think that taking the intersection of all these sets of Campana points gives us back just a set of integral points. So in a sense, we say Campana points approximate the set of integral points by taking parameters larger and larger. So what I want to do now is to measure these points and give you a conjecture about the distribution of Campana points, which is a generalization of a known conjecture about the distribution of rational points. And in order to measure my points, I have to define heights. So let's see. The first thing, to make notation easier, from now on, we only work with k, the field of rational numbers, and OK, the integers. And I'm going to have to fix a line bundle, and I take an ample line bundle. On my variety X. Now I can use this to define a way to measure my points. So the first observation, I'm working in the setting of toric varieties. My ample line bundle is also very ample because my toric variety is complete and smooth. And I have a precise description of the set of global sections of this actually very ample line bundle, which is generated by some oh well. How do I write this down for you? So the one thing that we do have is that we can write all our effective divisor linearly equivalent to my L as linear combinations of L sigma, where sigma is a maximal cone, and this gives us a nice set of generators for the sections, global sections of my line bundle. And these representatives sigma can be written uniquely in terms of the torus invariant divisors, where here we do have that these L sigmas are the unique represent. Somebody has a microphone on. So these L sigmas are the unique representative in the basis of the Picard group, which is given by the torus invariant divisors, the rho with rho, which is not array of the cone sigma. So every maximal cone of my fan gives us one set of such rays, and they correspond to a basis of the Picard group. Each maximal cone gives a different basis of the Picard group. And this is true because X is a smooth toric variety. Okay, so this L sigma is the unique representation of L in this basis. And altogether, they just give me some data, their coefficients, which I'm going to use to define my height. So the height can be written on the torsor or on the toric variety in two ways that are compatible. So on the toric variety, we just look at points, and then we get this linear system, a complete linear system of the line bundle L, and we get mapped to some projective space. And we use this basis of section given by the effective divisors that I just defined. And then on any projective space, we have a standard veil height which we can use by composition to define a height on X. And the height is just submorphism from the set of rational points to the real numbers, with a very nice property that whenever we fix some number here, then we have a finite number of points with height at most the given fixed number. We can write down the height very explicitly on the torsor. So here we have a map, and I'm going to call this one my height, because I'm going to use it later on. It is a map that sends a point to the maximum over all these maximal cones sigma of absolute values of monomials corresponding to these L sigmas. Now this would be just some product over all the coordinates y's and with exponents the coefficients of the divisor that I just defined as sigma. So here we're just taking absolute values as real numbers. Oh, I think that I said that I would work over Z and then I forgot. Okay, so this is Z. And this is Q. So it should be a little bit more clear. We're just looking at integers and then monomials of integers. There are integers again, and we just look at absolute values. Now that we have a height, then I can tell you what we can use it for. We have a conjecture. In joint work with Arne Smith, Sho Tanimoto, and Tony Varidi Alvarado. We can look at the number of points of bounded height. So this is really the cardinality of the set of points in my torsor, if you want, or downstairs in my on my toric variety. I can do this because this is a 2 to the R2 map. So it's a finite map. So it's a map with, it's a function with finite fibers and all of the same cardinality 2 to the R because of my choice of the base ring set and the fact that I have a GM to the R torsor. So in principle, the conjecture will tell me something about the cardinality of points of bounded height on this set, but for simplicity and for the counting that I want to explain later, I'm just working over this torsor. So we just look at points in here, such that yi is I full for every I. So this point lies in the preimage of the set of Campana points, and the height of this point is at most b, which is the same as requiring that all of these monomials have absolute value at most b. And then because of how we define the height, I can tell you that this is indeed a finite set. So this cardinality is a number. And what we're going to do is look at what happens to this number when we take the bound to infinity. So what the conjecture says is that this set behaves asymptotically as some positive constant b to the a of L log b to the b of L minus 1. Where a of L is the Fujita invariant of L in the Campana pair. So the infimum of real numbers T with the property that TL plus the canonical divisor of the toric variety plus the boundary divisor dm is effective. And B of L is the codimension of the minimal phase of the effective cone that contains the adjoint divisor A of L times L plus kx plus the boundary dm. So what this conjecture tells us is that we have a lot of arithmetic information about these points, but at the end of the story, all the arithmetic information is going to be contained in the leading constant of this asymptotic formula, and the rest is going to be determined by these two geometric invariants of the variety x, which were the, let's say, the parameter that defines the Campana condition, the mi's, they are all encoded in this special boundary divisor, which we wrote down. And so we also have a similar conjecture if we work over every number field, and still the two exponents don't depend on the choice of the base field. So these are really just geometric invariants. All right. So what I wanted to do next is to give you some heuristical ideas of why this conjecture should be true. And then the result that we have. So this is what I call the hyperbola method heuristics. So the hyperbola method is one analytic number theory technique to count, well, lattice points. So what happens is that here we are looking at points as tuples of integers. So these are lattice points. They have some special condition like this, and they have to live in the region defined by this other condition here, which is certain monomials up to a given bound. Okay, so this condition in here is what I will call the condition that gives me the region of summation. So it defines some space with sort of hyperbolic shape where I want to count my lattice points. And this hyperbola method more or less works by covering the region of summation by boxes, because we know how to count points in boxes very easily, but we don't necessarily know how to count points in weirdly shaped domains like the ones defined by our height. Then we want to count points in each box. And this is something that we know how to do. And then we want to sum the contribution of all the boxes. Okay, so how does this work? Suppose that we have a box, and
why is it hyperbola?
Hyperbola because so for me, because it is used to count points in hyperbola shaped regions. So perhaps I can give an example. So let me write down here an example. If x is P2, there's no hyperbola involved. The region of summation looks like, well, really just a box in A3. and there's nothing special going on in there. But if we go, for example, on P1 times P1, then the conditions where we want to count our points are something like xi, yj at most b. And now each of these conditions gives me something which looks like a hyperbola type of condition. Now this is just for the two chosen variables, and I have such things for each of the pairs of variables, and I have to intersect all of the conditions. So that's where the hyperbola term comes from for me. There are some other hyperbola methods mentioned in analytic number theory, of which I am not really an expert. But well, the term was coined by Blomer and Pruden, where they really were working on just products of projective spaces. And here the hyperbolic shape is obvious. And the main problem we have is that here this goes to infinity, this goes to infinity, this goes to infinity, and this goes to infinity. And we expect that at some point in this part towards infinity, we have no lattice points to count if we remove all the points that lie in here. But understanding how to deal with that and precisely at what point one has to cut these tails, it's not obvious. And so, yeah, what the hyperbola method does is to say, okay, then let's just put boxes everywhere and count in boxes, and then figure out which boxes are going to give me the main term and which boxes are going to contribute so little. I have so little points that don't really contribute to the main term, so we're going to put them into the error term, and they have a negligible contribution. Does this answer your question?
Well, okay, to some extent, yes.
Okay. All right. All right, so to get an idea of how this works, we look at one box and see what happens. So we choose boxes so that each coordinate has a given size. Say bi. What does this mean? For example, we can take some box where yi has to live in something like bi up to 2bi. And we take the bi's that depend on the bound b that we want to set to, that we want to go to infinity. So something like b to the ti, where ti is a positive real number. So ti is going to be fixed for my box, and my box depends on b. So if we enlarge b, I will have a bigger box. And then if we have one such box, so I can try to understand the contribution of this box to the subintegers. So how many points are there in one such box? And well, I'm trying to count points, but not just, so if I were counting just integers there inside, I would have more or less up to some constant bi for each coordinate. But because I'm counting component points, so I'm counting points with these mi fullness conditions, then I have an exponent of 1 over mi for each bound. And this is because the number of integers at most b and such that z is m full this is known to be asymptotic up to some explicit constant C, well, not the same as the C before, so let's say C prime, and B to the 1 over M. And this is a result by Erdős and Zekers. A very old result. So each of the sides of the box is going to give me a bi to 1 over mi, and the whole box is going to give me a product of these. And this is the same as v to the sum of the ti over mi I from 1 to s, where I'm just substituting now this expression bi is b to the ti in this formula. So this gives me one possible exponent of b contributed by the given box of the given size for b to the ti. So now there are two things that one has to understand. First, when does the box live into the area of summation that we're interested in? When does the box satisfy the height condition? So we say that the box is admissible for this counting problem well, if we want the ti to be positive real numbers, and then we want that the box is inside the area of summation, so we want to have that the sum of this alpha I sigma ti is at most 1 for every sigma. Why do we want this? So this comes from the fact that we want that our b, our bound, say b1 up to bs, to the L of sigma is at most b the bound. Okay, now I think I'm using too many b's. I'm sorry about that. So we are asking that all the points satisfy the height condition. A certain monomial has a size at most b, and then I'm putting my bounds into this condition, and what I get is that this thing here, which is product over I of bi to this alpha I sigma, and I just substitute the b to the ti for the bi, and so I get this alpha I sigma ti, and this is now what gives me this condition. This exponent is the smallest exponent of b, and this has to be true for all the monomials that gives my height, and so for all sigma. Okay, so whatever this means, these two conditions are just conditions on real numbers di, and they give me a polytope, say p, in R to the s. And the other thing that we have is that we are going to have in our main term of the asymptotic formula only the boxes in the region of summation that give the highest possible contribution. All the rest is going to be in the error term. And how do we measure the highest possible contribution? The highest possible contribution is given by the highest possible exponent of the box contribution. So in order to compute this number, we have to maximize this function. So we want to understand what is the maximal value of the linear function sum I from 1 to s of ti over mi on boxes that are admissible, so on the polytope P. And this is a linear programming problem. And what I prove in joint work with the Maris Schindler is first that this linear programming problem is dual to the linear programming problem, which is in the definition of the Fujita invariant. So that is a minimization problem in the definition of A of L, the expected exponent of B in the asymptotic formula. And then by strong duality in linear programming, the two problems which are dual to each other have the same solution. A of L. So the hyperbola method heuristics tells me that what the hyperbola method predicts for an asymptotic formula just by counting is that indeed the main term has a shape some constant times b to the a of L, which is what was also in the conjecture. And then we may have some other factor log b to some power. And this power here, the hyperbola method tells us that k is the dimension of the phase of the polytope P, where we have been doing our linear programming problem, where the function that we want to maximize has indeed the maximal value. And this is always a phase of my polytope. And then by working out the toric geometry behind this, what we show is that actually this dimension k is equal to B of L minus 1. Now I don't have time to give you the details about this. It is a very nice computation, but essentially what we are doing is writing down everything in terms of cones into the vector spaces in the space of divisors of my toric varieties, and working out all the conditions between the conditions for the boundary and the fact that L is a very ample divisor, and what does the height mean in geometric terms and so on. And we find these cones that are dual to each other, and then we can show that we have these kind of conditions. And then finally, last result, we also have a theorem besides these heuristics, still with the Maris Schindler. So we prove that the conjecture holds for what I write here, many toric varieties X, where many means up to some technical condition that we need for actually working out the hyperbola method as a theorem, not just a heuristic. And with a special choice of the ample line bundle to be the log anti-canonical line bundle that we're going to require to be ample for this theorem to hold. And if you're curious, in this case, what we have is that the Fujita invariant is 1, and that the other invariant B of L is the rank of the Picard group. In particular, this theorem proves the conjecture for X of Picard number bigger than the dimension. That's one of the cases that is covered by this theorem. All right. I think I should stop here.
Thank you. Just thank you, Marta.
Thank you.
Any questions? If not, I have a couple of questions. So first, so you say that you show that some dimension of some phase equals equals what you expect. But it do in fact show that so you have like two faces of two polytopes. One face of some polytope is defined as the face where some function attains its minimum, and the other is defined is a face of a toric polytope, which is defined in geometric terms like where your divisor lands when you move it to the effective threshold.
Yeah.
So do you really show that these faces correspond to each other?
Yes, that's what I do.
So it's not just the dimension equal to each other, but it's
No, they're really drawn to each other. I don't know if you want to see a small diagram that shows, I mean, it doesn't really show that, but this explains kind of the thing. So what I have is I have space of divisors. And I have the space of linear functions on these divisors on the other side. And these are dual to each other. And then inside it here, I have a map down to the Picard group, which just sends divisors to divisor classes. So, okay, this is space of torus invariant divisors. Okay, we have this map in toric geometry. So on the other side, by duality, we're going to have a subspace, which I'm going to call H, which corresponds to the Picard group under duality. So what one can prove is that inside R of S here, we have my polytope, which is defined by the conditions that I wrote down before, which is the one where we want to maximize a certain linear function. And what I prove is that the face where the maximum value is attained, because L is very ample, is going to be contained inside H. So inside H, we are going to have P intersected with H, obviously, and here inside, we're going to have our face F. And what happens is that my face F does not contain the origin of R to the S. It is some face out far away from the origin. What I can do is take the cone generated by this face. So we have all of these inclusions on this side. And so the other thing that we can prove is that this polytope is defined in a way which corresponds on the other side in here to the effective cone of X. And then under this duality, here inside, I have this face that defines B, so smallest face that defines the adjoint divisor. And what I show is that this one now is dual to this one cone here. And now this face here has dimension B of L by definition of B of L, and this one here has dimension K, and this one here, which is a cone, is dimension K plus 1. And this is how the dimensions match to each other. But what I really do is prove the duality under this first duality in here, and then in here, and so all the way down. And well, that's how the proof goes, just by checking that indeed the conditions on one side, it was very, very surprising for us because the Maris does a lot of this number theory stuff. And she was telling me, you know, the Hyperbola Method gives me this polytope. What is this polytope? And then I started looking into it, and this condition looked very similar to something that made sense in geometry. And I figured that indeed that they were these geometric things. And yeah, that was very, very nice to see.
Very good. And another question. So can you give more details about this many? So what kind of technical conditions do you need for a variety?
Oh.
Just maybe a rough idea of what kind of conditions.
Yeah. So one condition that I need is that this face in here is not contained in any coordinate hyperplane. meaning I'm going to give you an example in here. So for the projective space, if I write down my polytope P, it's just going to be a cube. And the phase where the maximal value of the function is going to be attained is going to be this one in here, which is just a point. And what the condition, the maximal phase is there, so the condition is satisfied, but the condition, the maximal phase is not containing any coordinate hyperplane. It means in particular, it cannot be, for example, this point or something like this or something like this. Of course, if I change my function, my linear function, I could make any of these phases become the maximal phase. So in principle, everything could be allowed. So that's one condition. It's not extremely restrictive, but that's the one that gives me the restriction that I choose this line bundle, because for this line bundle, I can assure that it is true. And also the ampleness condition together gives me that. And the technical condition is a little bit more complicated. It says that
this is not a condition purely about the variety, it's a condition about the variety and L and the line bundle L.
Yeah, it's a condition about the variety and L and the boundary divisor dm. Because for what I got, the variety is the variety. L defines the polytope, and dm, the boundary divisor, so the component condition, defines the linear function that I want to maximize. So all three are involved. And here I choose L depending on the component condition, so that at least this condition is satisfied if L is ample. But then the other condition is what happens if I have some polytope. So of course in this picture, this is the nicest picture possible, and we don't see any pathological behavior happening. But the other thing that we do is at some point in the argument, we have to slice our polytope with the coordinate hyperplanes. So we take some conditions like Ti is epsilon I for epsilon very small, but not 0. And then what happens when we have these and we take epsilon I that goes to 0? So we look at maximization of the same function, but now with these extra conditions, and we are working in lower dimensional polytopes. And what we ask is, how big is the dimension of the phase where the maximal value is obtained in these lower dimensional polytopes? And we want that the dimension of this phase is smaller than the dimension of the phase where the maximal value is obtained on the whole polytope, this F in here. So there are two things that can happen. The maximal value is the same value, and because then I'm slicing this phase, then the dimension is going to drop at least by 1, and then I'm happy. But it can also happen that the maximal value on these section polytopes is smaller than the maximal value on the whole polytope. And if it is really smaller, meaning say A of L minus some fixed epsilon, so smaller than something like this, then I'm going to be happy. But I don't want to have the possibility that when my epsilon I goes to 0, then the new value tends to the original value. This is going to break out the argument. So the condition is that there exists some epsilon such that either the value on a sliced polytope is smaller than this, or I know that the maximal phase where this value is obtained as dimensional at most k minus 1, so smaller than the one for the main term. So this is the technical conditions that we have. It's really technical. It really has to do with how we do the counting.
And suppose that your theoretical right has large Picard number. So, and suppose that you pick L so that it is roughly random in this Picard group, Picard lattice. Am I right that in this case, the technicalities are going to hold?
So if the Picard number is large enough, because in this condition, I'm going to slice not just by a hyperplane, I'm going to slice by choices of as many as I like of these. And so there are two cases where the thing is nice, and we have some condition where these two cases cover all cases if the Picard number is large enough, meaning the dimension of my polytope is very large. So the answer is yes, we do have that condition for arbitrary L in that case.
Okay, thank you. Are there any more questions? If no, let's thank Marta again. With many coincidences.
Yeah, thank you.
Uh,
Thank you.